Hi everybody, my name is Bob, also known as Mingla, and here today I'm going to present the Q-learning versus SARSA, which is my HD task for the SIT 320. So I will firstly walk through a bit about the content I'm going to do today, which is firstly I start with what is reinforcement learning, um, and then actually I go deeper into what is SARSA and what Q-learning as a classic method of reinforcement learning. Then actually, I will do main point of the presentation is actually comparing Q-learning versus SARSA in theory anyway. And then next, finally I actually introduce the taxi V3 environment. Actually, is an implementation environment for me to actually have actual comparison between Q-learning and SARSA to see how they actually perform in real scenario. Sure, cool. So firstly begin what exactly in reinforcement learning. So I have a quite nice quote here from Alan Turing to actually tell that we need to break our mind from the idea of AI and in form of artificial intelligence is that it actually a form of adopt mind, like a smart exactly human mind. But actually we can shift our focus to thinking like we can actually have an actual child and like an actual human being and actually can do the training on it. So that's the idea of reinforcement learning. So it is a machine learning type, but it learns via the reward system. And the machines often start out with actually almost zero knowledge about the world, the environment. So it's basically like a child, and like it actually and start keep learning with the reward system. For example, it actually have the correct behavior, it actually have the positive reward, or it actually have incorrect behavior, it have negative reward, and that's how actually it got much better. And of course, this is actually very different from other machine learning like supervised learning or unsupervised learning is that it actually direct interact with the environment, which actually can be another issue or another cool thing about reinforcement learning is that actually can make change to the environment, so that it very similar to how child actually learn. And the problem to solve will need formulated in macro decision process. This will actually go deeper in the next slide. So macro decision process is a way to actually formulate the reinforcement learning, and is a very fancy name. So that's how we actually formalize the whole thing, as like we need to break through the whole thing in the system into two entity, as the agent and environment. The agent and the agent can actually make actions. The action can affect the environment. The environment will actually have the state, and the state will spit out the reward that go back to the agent. So as you can see that in the image here. So like have, for an example, we actually have a robot for a navigation task that's going to go to point A to point B. So the agent in that is is a robot, and the environment is the environment that's the robot inside. So the agent operates inside the environment. So the state can be like X step if we actually can divide these environment into different grid. And also we actually the agent can do the action as go up, down, left, right. So whenever the agent perform an action, so it actually may affect the environment. That actually it can fall down a obstacle, for example, and that will actually tell back to the agent with a reward and the state. That's the new what is a new state of the agent now, because if the agent move up, it actually go to a different state than the agent were before. And from that, the agent actually can calculate what exactly is the final reward, and it's that actually update its behavior. So it's like learning, yeah. So it keep interacting until it has the optimal policy. So the policy is a technical term in reinforcement learning to tell that it basically is like the brain of the agent to actually, okay, no, I know what I need to do next. When in the next stage, what action should I make? So normally with this, the classic way of doing it is actually to be discrete data. So like there will be discrete state and discrete actions. The agent can only have action, like for example, in the example as I told you, can just go up, down, left, right. But like in reality, we actually this actually is also the way a classical learning SARSA actually behave as well. But like in actual reality, we may actually have continuous data. So as it's like the for example, instead of going up, down, left, right, it actually can go in a circle. It can go whatever way it's like. whatever action you can make. So being like that is much more difficult, and it's not, I'm not going to cover that today, but there's actually a way for doing that nowadays. We call such as deep Q learning, when people actually by deep learning, which is the normal reinforcement learning, that actually solves the continuous data. Okay, so that's the whole basic idea. Now we go deeper into its algorithm. So the first one is SARSA. So SARSA, the basic idea of SARSA is learning from the current. So it have a Q table. So Q table is basically like the brain of the agent. So agent will always have that brain inside it. So it have a Q table. The Q table is basically a mapping between the state and action, and have each of them, each pair of state and action will actually have a Q value, which actually determine how good it is to be in that, to do that state. So the word it would be like how good it is to do the action in that state. Okay, and so the job of SARSA, as the job of the agent, is keep updating the Q table to actually have the final Q table as the optimal policy. So in the future, whatever state the agent will be in, it will actually will know what the best policy it can do. So to calculate the Q value, you go see here in the SARSA is this part here. So the way it calculates the Q value is actually by actually combining so here's our reward. But here's the thing, is actually from the next state and action. So this will be the key difference between SARSA and Q-learning, which I will we actually explain later. So you can see in the algorithm is do very normally. It actually looks through X episode. Well, we need X episode to actually do the training. So for example, we have 1000 episodes. The initial episode when the agent actually have absolutely no idea about the world, and the actually later episode when the agent actually have the better Q table. So like when we say optimal policy, like we never actually rig the actual optimal policy in some sense. We will converge, like actually go to almost optimal policy. The more you do the training, the more episodes you have to do the training, the better the agent will be. The smarter agent will be. That's what I say. Okay, now so this is very normal, but here's the key thing actually when actually it actually from the X step episode actually it takes the action it takes the action A slash from S slash as well. So actually after it go into the next state, it actually choose the next action as well, and actually it combines those things to actually devise the Q value. So that's the special thing about SARSA. So it actually stay on the current policy to actually find the next, to actually see what the next action would be, and actually have the value from that. And because that way, SARSA is a bit less popular in Q-learning, which I will explain now. So Q-learning is very similar, but we have the Q table and keep updating the Q table as well. But now the Q value actually derived from the best action of next state. So if you actually go to the algorithm here, you will see that now. So instead of choose A from S using policy, so it's still the same thing, but actually take action A opposite RS. This true action from S actually inside the loop here in the Q-learning instead of outside, like in the SARSA. And also there's no choosing the next action in here. So in Q-learning, is actually why in SARSA is the next action is being chosen right away in the same loop, but here for the Q-learning it doesn't do that, and instead actually when it updates the Q value, it actually picks the max action from the Q table. So that's why it's called, I say Q-learning is called being greedy. And actually by doing that, Q-learning often show in reality often have better performance, and that's why it's more popular. So that's Q-learning. So now actually I'm go deeper into comparing SARSA and Q-learning, which is the main thing of the whole presentation here. So like say the biggest difference you can see here, so in SARSA when actually do the updating for the Q value, SARSA actually updated based on the next action and state. So this is the action, next action and state. Why? For Q-learning, it's actually only update the next act, which is the next action and the best next state and the best action that in that state can make based on the Q value. So link back to the Q table. So like this action here, that's max. So the state is definitely the same state. The next state. So this the state here is the same, but the action here actually the best action, which is different from the actual action it can actually make. Here is the actual action. Okay, that's. And now we actually go deeper into theory. We actually call what SARSA do is on policy, while what Q-learning do is off policy. Because SARSA actually based on the current policy having right now, like the actual table is actually having right now. But Q-learning actually it changed the table. Now, so that's everything is basically what I say. So this the key thing here is actually make SARSA. Well, because of that, actually make choose the application of SARSA Q-learning very different as well. So SARSA convert to a solution that optimal under the assumption we keep following the same policy. While the Q-learning actually so actually based on the assumptions after generate experience training, we switch to over the greedy policy. So like Q-learning is greedy, so that's the basic thing. And because of the SARSA is very mindful about the next action. So it actually prefers situation when we care about the agent performance during the process of learning. For example, actually in a very hazardous environment. So we don't actually, for example, we don't want the robot. So back to example robot navigation. We don't want the robot to fall into the cliff. So in that case, SARSA will actually be more helpful because actually very mindful about the state and actual and current state. It actually can help avoid the hazard. Why Q-learning? Why? Because being greedy is keep doing what it thinks is the best, with especially in the initial state when the Q-table haven't been very finalized, when not very optimal, and it's just like going randomly. The Q-learning is very can be actually a bit dangerous. You can actually make this agent just doing a dangerous behavior to actually learn the best way to actually have the best result in the end. So because of that, Q-learning often used in the case that we don't really care about the agent exploration phase, when we just let the agent do whatever it needs to actually have the final result. For example, if we actually have a ping pong battle and we need to practice and lose a lot in the initial state, so we actually can win later. Okay, so in that case, Q-learning is the best. So that's why Q-learning is much more popular in most many problems that require it. Often it's like that. It's actually not really have any hazardous environment. Yeah. Sure. So now go to next one is actually go to taxi EMV3. So it's actually the environment I'm going to use for the testing of this issue to actually see the difference between SARSA and Q-learning. So the goal of the taxi inventory is actually from spot to actually see on the picture here. The 4 spot, and we actually the 1 spot each of there will be a customer in one of those 4 spots, and the taxi will try to pick up the customer and take him to the goal destination, which is at another spot. Yeah. So in here, so that's a problem, and now we need to break it into the marker decision process. So firstly, we actually have the action. So the agent is a taxi, and actually the 6 actions the agent can make. So actually move up, down, left, right, and pick up and drop up. Now, and for the environment, we actually have 500 states. So it's not just like 25 states, like 5 times 5 with a grid, but we actually need to consider the 5 possibility of the passenger location as well, which is the 4 location and is a taxi, and also the 4 destination as well. So that's something very mindful. Like sometimes the state is not that obvious as like this grid. We also need to consider other aspects as well. And finally, if the car reaches the goal, so that's the next one is actually the reward. That's how we actually do the MDP. So the reward, if the customer actually reaches the goal, the reward will be 10. If the car move into the wall, it gets reward minus 10. And if there's anything on the thing, it's just minus 1. So that's how the reward system works in this case. And the final thing is the result. So after let the agent run through the result, we actually have let the agent run to 1000 episode, and we actually see how it goes. And each episode, the agent have to reach the goal. So we actually have 3 ways to measure it. So the first thing is the epoch. So like at each episode, please note is that like after each episode, the agent got smaller because the Q table got updated. So each episode, we measure how many epochs, so how many steps it takes for the agent to reach the goal. So here we can see that Q-learning is actually do very well. SARSA actually do a bit better in the beginning, but in overall and in the end, Q-learning actually do much better than SARSA, and it takes much less step to actually reach the goal. So the curve very strong for Q-learning, while SARSA is different and that is a bit more noisy. The next thing we measure is the accumulated reward. So as each episode, we see the total reward after the whole action, how actually what is like. So again, Q-learning is doing much better. SARSA do a bit better in the beginning, but after that, Q-learning is totally overwhelmed SARSA. And the same thing we can see the last one. We actually see the number of times the Q-learning and SARSA bump into a wall. And SARSA in this case surprisingly actually do better than Q-learning. So they actually can be explained because that's the environment, and they actually can be the noise of the data, or actually there's not enough data to see it. The problem is too simple. So if you look at this, you see in the end, both of those SARSA and Q-learning actually convert to almost the same result. So it actually go to the same optimal policy here. So it's very similar in the end. But like here, during the whole phase and in the general, Q-learning in all three measures actually do better than SARSA. So we actually can see why is Q-learning actually do better. Sure. And that is for today for my presentation. Thank you for listening.